right, so let's talk a little bit about assigning oxidation numbers. This is the foundation for basically all of electrochemistry when it comes to what's a redox reaction, where are reductions happening, where are oxidation's happening. And so knowing these rules is really, really important, and being able to just kind of looking at an element and looking at those polyatomics and just knowing what those oxidation numbers are very, very important. So, there's a lot of rules out there, and you can find a bunch of rules on the internet, and they're all kind of the same, but sometimes they can get a little bit overly complicated. So let's see if we can go ahead and simplify this a little bit. So, let's get into it. All right. So the first rule you have to think of is looking at free elements. So free elements have oxidation numbers that are equal to 0. And when I talk about free elements, I mean something, think of your diatomics, like oxygen gas in its standard state, or hydrogen gas, or even something just like carbon, right? So if I talk about like graphite or diamond, that's just made up of just, solid like carbon, carbon solids. So, just in the same rule, we can say that elements have an oxidation number equal to their charge if they have a charge. So what I mean over here is when you have ions. So let's say you have aluminum +3 or an iron +3. These oxidation numbers are going to be +3. So it just depends on if you have an ion itself, you want to just look at the element and look at the ion, that's going to be the oxidation number. The second rule, and notice these rules are going to be ever increasing in priority. So right here, we can say that they are increasing in priority, which basically means that first you got to look at rule number 1, and then you can go ahead and see, once you figure out in your compound rule number 1, move on to rule number 2, and then 3, and so forth. We can talk a little bit more about that later, but alkali metals, so when I say alkali metals, I think of your first row, so like sodium plus or something like that. Basically these have an oxidation number that's equal to +1. Now the third rule you want to talk about is, I guess this doesn't have to actually be an ion, but hydrogen. This is a really, really important one because it comes up a lot. So hydrogen atoms have an oxidation number of +1. Now, all of these have buts. So alkali metals have an oxidation number of +1 unless it's negated by rule number 1. Hydrogen atoms have an oxidation number of +1 always. So we're always going to say, when you look at something that has a hydrogen, it's just to go +1 unless you have rule number 2 or rule number 1 that kind of conflicts with it. So you always want to look at rule number 1 first, and then go ahead and try to puzzle piece the rest of them together. And that's what kind of that priority comes into play. The fourth one talks about oxygen. So oxygen atoms are going to have a oxidation number of -2, right? Unless you're negated by, like I said, rules, whatever's above it, 1, 2, or 3. All right, the fifth rule is that as you increase this way from the periodic table, so you're gonna, I'll just write increasing to the right, and I'm talking about groups 1, 2, and 3. We're going to have oxidation numbers respectively of +1, +2, and +3. So anything that group 1 is going to be +1, which we already saw from rule number 2, and then +2 and +3 and so forth. Going this way on the periodic table, if oxidation numbers are actually going to decrease going to the left of the periodic table, starting from kind of the right end. So I'm talking about group 5, or yeah. And then this group, so we're going to go from -3 on the super right side of the periodic table to -2 and then -1. And then we are going to say just the last one is anything that's left over. So any leftover atoms, you're going to assign oxidation numbers depending on the others around it. So we're going to look at all the other rules first, and then you're going to use whatever's left over to assign the oxidation number. So basically the bottom line is to keep the charge on the compound. So let's say you have something like K2HPO4. This overall has a 0 charge, which means it's neutral. So we can just go ahead and look at these rules and say, how are we going to assign these oxidation numbers? All right, so the first thing I can say is that hydrogen, this is kind of or actually I can look at my alkali metals. Sodium or potassium is an alkali metal, so this has a +1 oxidation number. Notice there are 2 potassiums, but even if there are 2, you're going to look at oxidation numbers are just dependent on one atom. So one atom of potassium that still has a +1 charge. So these are going to be my oxidation numbers. All right, so basically, because there are 2 of them, we can say, okay, the oxidation number is +1, but this contributes a +2 charge. And then hydrogen, we can say, all right, rule number 3 says hydrogen is also a +1, cool. And then rule number 4 says oxygen is a -2. So let's look at what's going on. This contributes a +1, this contributes there's 4, and each one of them is -2. So there are 4 oxygens, and each one of them has a -2. So this contributes a -8. And so overall, what we have right now is a -8 plus 3 charge, which is a -5 charge. However, because our total compound is neutral, we can say that phosphorus has to be a +5 charge to kind of negate that -8 so that we can keep our compound neutral. And if this was a -1, we can do the same thing. So this was K2HPO4, this was a negative, this would still be +1, this would be +1, this would be -2, but this in this case, phosphorus would be a +4. So these oxidation numbers are not dependent on the atom, they're just dependent on the charge of the compound and what's going on. And that's kind of the fundamentals of these redox reactions. So let's see if we can do some examples. So this is where I would pause the video and see if you can do them as I do these examples with y'all. All right, let's look at, I'll try to keep this over here so y'all can see. All right, let's look at, whoopsie. All right, let's look at sodium and hydrogen. So this is kind of an odd one, but it's a good example. So the first rule we have both hydrogen and sodium rules on our 6 rules that we have. But sodium has a higher priority because it's an alkali metal. So I'm going to say, okay, that's a +1. Now this has a neutral charge. I'm just going to write a 0 because it's not negative or positive. So this hydrogen has to be a -1 in order to balance that out. This is kind of unprecedented, because you might think hydrogen as a -1 is weird, but it is what it is. You have to follow through with these rules. All right, try to do hydrogen gas. Now hydrogen gas, it is a free element, so it's going to have an oxidation number of 0. All right, let's do H2O. All right, so you might be tempted to go ahead and put a -2 on the oxygen, but always go through these steps. Hydrogen always comes first, so +1 on that hydrogen as my oxidation number. Contributes a +2. So yes, because of this, our oxidation number of oxygen is a -2. This oxygen functions as a leftover atom, trying to make that compound neutral, rather than just obeying rule number 4 right off the bat. All right, this one's a little weird, so let's go ahead and look at it. Sodium and then 2 oxygens. The first thing I want to think of, once again, is sodium as alkali metal, so we're going to say it's a +1. And because of that, oxygen, to keep it neutral, has to be actually a -0.5. Yep, that's weird, and you probably won't see that super often, but you know, it's just going through these steps and seeing if you can kind of understand where everything is coming from. All right, ZNO, try to go ahead and do that. So oxygen has a -2. All right, zinc doesn't have a rule by itself, but it does function as a leftover atom over here. So I can say this can be a +2 charge, keeping this electrically neutral. This one kind of shows up a lot, so let's go ahead and do that. I don't know, chemistry professors love this one. So sodium, manganese, and oxygen. This is kind of like the one we did earlier, but potassium is potassium, sorry, I don't know what I said earlier, has a +1 because it's an alkali metal. Sodium has a -2 because of rule number 4. So right now we have a -8 charge going on and a +1 charge going on. And this is actually neutral, so we can say this manganese has to have a +7 charge in order to balance out and keep it neutral, because right now we had that -8, -7 charge. Now this can be -1, -2. A lot of stuff can happen with this, so just be aware. Another good one maybe is methane gas. In this case, we look at hydrogen as the rule. So hydrogen is a +1. That contributes a +4 charge. Remember, this is not the oxidation number. And that's the biggest thing that I see students kind of struggle with. This is not an oxidation number. I'm just saying this is how much charge it contributes. All right, so in this case, in order to keep this electrically neutral, this has to be what? Because there's just one carbon involved, it has to be a -4 as the oxidation number. All right, let's do one more to kind of drive in these rules, making sure you're looking at them. H2O2. All right, this is not going to be the same as water. So the first thing you want to look at is hydrogen. Hydrogen has a +1 charge. There are 2 of them. So it contributes a +2. So our oxygen has to contribute a -2. In order for it to contribute a -2, one oxygen is going to have a -1 charge. And this -1 is going to be our oxidation number. All right, cool. I hope y'all enjoyed that and it was helpful and y'all learned something. So comment below if you have any other questions or any other videos you want me to make.